Okay, so this is a subset of the polar graphs, limacons and lemniscates. That's not actually a C, I guess it's called a cédille in French. It's some kind of funky French C. Am I saying it right? Limacons. Limacons. Okay? Yes. Okay. Now, when I okay, hang on, let's go. Okay, so limacon equations, there involves a sum out front. So just to remind you what we know, sine of theta is just a straight up what? Circle. Okay. Sine of 2 theta, when you put a number in front of the theta, that makes a rose. And depending on whether the coefficient is even or odd, you might get same number of petals or double petals, right? Now, today's a new kind of change or transformation to the graph. Now, it's important to know, first of all, that transformations in polar are totally different than transformations in functions. When let's just go, say the graph looks like, so if I said the graph looks like this, 2 pi, 2, let's go 3, and so on, -3, right? If I said, what does this do? Then what does that do? It doubles what? So multiplying causes what kind of transformation? Shift, reflection, or stretch and squish? Stretch and squish. Okay, in this case, is it stretch or squish? In horizontal, stretch or squish? Horizontal, squish. It makes the period smaller. Okay, if I took this, which was 3 sine of normal x, and now I made it 3 sine of 2x, now the period is 5. Okay, now that said, though, you need to understand that the shape of the graph is not changed. It's still a sinusoid, yeah? That is not true in polar. In polar, if you go from here to here, the graph is a totally different nature. Now it's not the same shape, it's a rose and a circle. So multiplying in polar changes the graph 100%. It's not just a kind of a tweaking of the graph, it's a total change. The same goes with adding, which is the topic of the day. When I add, that will not shift the graph around. No. It will actually change the graph a lot. And I actually teach this differently than I would teach this. If I taught y equals 3 plus cosine of x, if I were a pre-calc teacher or algebra 3 teacher, and I wanted to teach you what the 3 does, I'd probably say, here's what cosine looks like, and then when you add 3, it shifts it up 3. But I would think of cosine as the base graph. And the 3 does a little changing. Yeah. Are you with me? Yeah. Okay, now I'm actually going to flip that a little. And on polar, today you'll get an equation like that. And I think it's actually easier if you think of this as the base graph and cosine as the thing that's doing a little changing. Now, if you graphed r equals 3, it looks like that, I think. You'll agree? Okay. Now, when we go to change the graph by adding a cosine, let's consider how it will change the graph, keeping in mind what r means is distance from the origin. Yeah? Yes. Now, I think you'll agree that when you add the cosine, if cosine is positive, then what? Well, if cosine is positive, then r will get bigger or smaller? If cosine is positive, isn't 3 plus a positive a bigger number?
Yeah.
Okay, so if cosine is positive, then r gets bigger. And my curve then, instead of being at the circle, will be outside the circle. I'm going to go further from the origin. So I will go further than the circle, which is to say outside the circle. And if cosine is negative, then 3 minus a little something will be, I'll go a little less far from the origin, so I'll be inside the circle, right?
Yeah.
When cosine is negative, inside the circle. Now keep that in mind as we go here. All right, so let's start here at 0. At theta equals 0, remember it's a total thought process in polar. When you face this angle, you find out how far you go forward or backwards. At theta equals 0, how far do you go forward?
3.
3 and 1 or 4. Yay? So you can see that in terms of, I'm going to dot this. In terms of that normal base graph of r equal 3, I went out actually a little further than that. What about all these angles? And here, cosine is positive or negative?
Positive.
Positive. So I will continue, every one of these angles that I face, I will continue to be outside that r equal 3, a little more than r equal 3. You with me? But I think you'll also agree that as I turn this way, cosine doesn't stay its max of 1, it gets smaller and smaller. So as you go this way, r will get a little less than 3, oh sorry, just a little less than 4, then a little less, and a little less, and a little less, until you get to pi over 2, where cosine is 0, and then r is just straight up 3, or 3 plus nothing. So in here, the first quadrant equals the circle is stretched out. Now, what's going to happen over here? Because cosine is negative, we will now be less than 3, so we'll be inside the circle. So a little less than 3, and a little less, and a little less, and a little less, until you get to pi over 2, and that is?
It's negative 1. 2 to 3, so it's 2.
2. Right? Actually, so it should have collapsed quickly. So it should actually take on this kind of egg shape. Now, these down here are going to be the same as quadrants 1 and 2 by symmetry. We have talked before that sine curves are symmetric about the x-axis, so you'll see those same results here, so it'll go back to that. Now that is a stretched kind of circle. It's a little bit egg-shaped. It's a little pointier here and a little flatter there. Are you with me?
Yeah.
Okay. Now this is one of 4 types of limacon. There are 4 types of limacon, and they're all based on how big that number is out front. When that number is much bigger, 3 is a lot bigger, and so the cosine doesn't have a huge effect. It has a little effect, but not a huge effect. When the first number is much bigger, and by much bigger we define that as double or more, then you get this convex limacon, egg shape. Okay? Are you down? All right. Now let's try if we gave the cosine a little more oomph, a little more power to change the graph. Now, say you are going to graph r equal 3 plus 2 cosine. Again, think of r equal 3 as the base graph. Now we're going to add, instead of just adding a cosine on to it, we're going to add a 2 cosine to it. And so it'll affect the circle even more. At the pi over, or sorry, at theta equals 0, what's r? What's cosine at 0? 1, and therefore r is 3 plus 2 times 1, or 5. Okay, so if we take that base graph of r equal 3 here, we really stretched it out because the cosine is stretching it even more now. And now we're all the way up to 5. We? Now, in here, cosine is still adding some until we get to pi over 2, when cosine is 0, and there r is just 3. So it goes from more and more stretched to less and less stretched until it's just at the circle because the cosine isn't doing anything at pi over 2. You follow?
Yes.
All righty. Now, in the interest of accuracy, I'm going to do a pi over 4 here just to get a good feel for the graph. At theta equals 3 pi over 4, r is 3 plus 2 times what? Negative or positive root 2 over 2? Negative root 2 over 2. Read?
Yeah.
So this is 3 minus root 2. Anybody know what root 2 is about? 1.4. It's about 1.4. So this is about 1.6. So when you point at 3 pi over 4, would you go forward 1.6-ish? Follow? Now what about back to the axes? At theta equal pi, what's r? 1. Now that means then that now the circle is being stretched in so much that it's getting sucked into itself, and you're getting a little bit of a dimple. Now use symmetry again. Go maybe 1.6 and back to 3, and then back to 5. Now, when there's a little bit of a less of a difference between these two, then you get a more extreme effect on the circle, and you get a limacon that is concave. It's got a cave to it. If I drew, concavity means that if you drew 2 points in the figure, if you draw a segment that leaves the figure, it's concave, not convex. So you have a concave limacon. Now, what distinguishes one from the other? Well, it has to do with how these numbers relate. When you did r equal 3 plus cosine theta, the 3 and the 1 in front of that, the cosine didn't have much of an effect. So it was convex, just kind of an egg shape. Are you with me? But when you give the cosine a little more power, you start to cause a little more sucking in, and you get a concavity. Now let's continue on. Let's say we give the cosine a little more power, like equal power. Instead of the first number being way different, now the coefficient and the constant are the same. Well, if you consider the base graph of r equal 3, and then what the cosine will do, at pi, or at 0, excuse me, at theta equals 0, what's r?
R is 6.
6. 1, 2, 3, 4, 5, 6. Rough it in. Okay? At pi over 2, what's r? 3. So we went from really stretching the circle till not stretching the circle. Now we're going to start to get negatives. So we're going to be below or inside the circle. Do you agree?
Yes.
What about at pi? 0. So it goes from going forward 3 to going less forward, less forward, less forward until I go not at all forward. And then by symmetry. Okay? You with me? Now this is a limacon with a concavity. I think you'll agree this is also concave, yeah? It's got a concavity in it. But what makes this special is if it goes all the way to the origin. Then it is a cardioid. Cardioid is some kind of, I don't know, Latin or something, Stemish for what? Heart, yes. It's a heart graft. It's important to learn this because Valentine's Day is coming up. This is how you're going to send your math Valentine a Valentine. It is a heart. It is not a butt. Every year, oh, it's the butt. It's the butt. It's not a butt. It's a heart graft, not a butt graft. Oh, baby. Know where your heart is. All right. Now, what really makes it cool is then when you give the trig a lot of help. This is, to me, one of my favorite graphs. This is super cool. So, if r equals 3 is your base graph, now your cosine is going to really have some effect because it's got even more power than the circle. So this one we'll go through a little more slowly so you can see it unfurl. So let's say at theta equals 0, r is 5. What is it? 8. So I keep your scale of 1 because I want the graph to be nice and big. 1, 2, 3, 4, 5, 6, 7, 8. It would be way over here, yeah? Yeah. Okay. And what about at theta equal pi over 2? R is 3. So we went from way stretched out to less and less stretched out and less stretched out until we get to pi over 2 when the cosine doesn't do any stretching out and r is just 3. You with me? Mm-hmm. Cool. Now, let's again consider 3 pi over 4. At theta equal 3 pi over 4, r is 3 plus 5 times negative root 2 over 2. And 3 plus 5 times negative root 2 is about 1.4 divided by 2 is 0.7. What is 5 times 0.7? 3 minus 3.5-ish, so it's about negative 0.5. All right, now consider then, first of all, what's going on there and what went on in between. When I face 3 pi over 4, what does it mean when r is negative? It means I don't go forward that direction half a unit, I go backwards. So I actually end up here, right? Now, what? So I'm facing 3 pi over 4, so I'm at the origin facing that way, but I go backwards a half a unit. So I end up there, right? Now between them, think of the intermediate value theorem. Could r have gone from a positive 3 to a negative 0.5 without first going through 0? Yeah. So this should have been going forward 3, then a little less, then a little less, then a little less, until you are going, there must have been a place where r was 0. And then you started backing up. So you actually went forward less and less through the origin. Now we're backing up. And when we get to pi, when theta is pi, r is negative 2. At that point, I'm backing up all the way to negative 2. You see? Right? And then by symmetry, that's as far as backwards as I ever go. Because that's the least cosine is when cosine's negative 1. That's the farthest I back up. Then, as I face these, I'm going to back up less and back up less and back up less until I get back to 0. And then I start gradually going forward, forward, forward. And so you start to get a limacon with a loop. Limacon avec loop. Okay, And what happens in the equation to make that? Well, if the second number is bigger, you get a loop. You get a loop. Notice that the max distance is the sum of the two. And the loop distance is the difference in the two. The max distance is the sum of 3 and 5, and the loop is the difference, 3 and 5. The loop distance is the sum of the two. You follow? Okay. Alrighty then. So, we noticed, I hope you noticed, that all those cosines are symmetric at the x-axis. Sines are symmetric at the y-axis. Use that. When you get a limacon, the first thing you decide is it a limacon, a rose, a circle, a spiral, a line, etc. What makes a limacon equation is it's of this form. Number plus number cosine, or number plus number sine. Understood? First thing you have to do is recognize the equation as a limacon. Second is you need to decide, all right, what kind of limacon, and that's based on how the two numbers relate. If the first number is much bigger, it's an H. If the first number is only a little bit bigger, then it's a concave. If the numbers are equal, it's a cardioid. It goes all the way into the origin. The dimple goes all the way into the origin. And if the second number is bigger, it's a loop. Okay? And then, last but not least, use symmetry and sketch accurately at all the pi over 2s. I don't ask that on your homework you graph the pi over 4s. Just at the pi over 2s should do it. You should be good. All right? So, would you give those... do you want to walk through the process then real quick? Let's do one together. Okay? So, is this a limacon? Yes. Symmetry at the x-axis or the y-axis? Y-axis, because it's sine. What kind of limacon? Convex, concave, cardioid, loop. Doesn't go all the way into the origin because these aren't equal, so it's just a concave or dimple. All right. So I would expect a concave limacon symmetric at the y-axis. Now let's graph it accurately. At 0, what's r? 3. At pi over 2, what's r? 5. At pi, what's r? 3. At 3 pi over 2, what's r? 1. Okay, so now we're going to graph a concave limacon. And so it should look something like that. It should have a concavity to it, and it is not a butt. Okay? Try the next one on your own.
Touch the boat. But
Ready? Do you agree it's a limacon?
yeah.
Do you agree it's symmetric at the x-axis? Do you agree it's a loop?
Yeah.
Okay. So you should be at 4 to start with. Then getting smaller and smaller and smaller until at the y-axis it's 1. Then you start getting smaller and smaller and smaller until you get through the origin and back up to -2. Then get closer and closer to the origin So you get back to the origin and then curve back through the negative y-axis. And so you should have points on the x-axis at 4 and 2, and the y-axis at -1 and 1. Is that what your graph looks like? Try the other 4, excuse me. 4. Yes, and I'll be walking around. Let me know if you have questions. Yes? Who said it this room? Oh, who said this room? Oh, huh. Yes. Why must you go through the order? Good question. At this point, I know r equals 1. And at this point, I know r equals -2. At all these angles in between, they exist too. And r can't go from 1 to -2 without passing through 2. That's why I know it has to put the origin somewhere, and then it has to have an arc. Okay. When you get a positive or negative in there, sometimes you'll get a little flipping. The third one, your Valentine's Day, right there. R equals 2 minus 2 cosine theta, or sine theta.
I see how it's considered.
Yes. It's like pretty clear.
No, that's like my life. It's not real.
Because all these signs these signs are positive numbers. So it goes from r equals 2, and then I subtract it until it's a little less than this, so I'm going less and less far up from origin, so I go into the origin because at theta equals 2. You actually start to get a little bit further out, and it's down here, Yes. Yes, sorry. Okay, are we ready? Okay, 4. What do we got there? Limacon with a concavity, a dimple, or sorry, concave, convex, what? The first number is much bigger, so it's convex, all right? Think about it on the extreme. What if you did this?
It is basically circle.
It's basically a circle. What?
Does it-
very
but it
small
does that little
stretch.
shit.
This does practically nothing to the circle. It's adding and subtracting very little. This is practically circular, yeah? That's what's going on here. This first number is so big that this cosine's not having as much of an effect. I think you'll also agree I need to change the scale here. So let's go by twos. What do you think? Okay, at 0, what's R?
What? R6.
6, 2, 4, 6 there, okay? At pi over 2, the cosine is 0, so it's just 8. At pi, that's -1, and 8 minus 2 times -1 is 10. 2, 4, 6, 8, 10. Now, when I say 10, I mean forward 10. You're going forward in that direction 10 units. Remember the nature of R. And then here is 8 again. Yes, 2, 4, 6, 8. And so this is egg-shaped. It should not have a dimple to it. You with me? Okay. This, what kind of figure? What kind of limacon? A loop. It's a loop, and symmetry at the y-axis. So it should be at 0, you go forward 2. At pi over 2, you go forward 6. That's okay. At pi, you go forward 2. And then once you get in here, you start backing up. At 3 pi over 2, where do you go? You don't go forward 2, you go backward 2, yeah? So you actually should be backing up and get a limacon avec loop. Oui? All right, and then this. This is also this is the first number is much bigger, so it's more of an egg shape. Are we cool? I'm going to go by twos again here. So it should be 6, 4, 6, 8. And egg shape. How'd that go? All right, cool. Hoping today I get caught up. But you guys have 3 sets of homework questions, so I don't think it's going to happen. I'm going to blow off area again and go to lemniscates. All right.
It's okay, we can catch up on Monday.
I will get caught up, doggone it, come heck or high water. All right. So, lemniscates are a little bit of a different graph here in that you've got a square. The first thing that I see when I see a lemniscate is R squared. Kind of different there. All right. Now, you could think of this as plus or minus 4 square roots of cosine. And that kind of helps a little, but let's talk about it. Okay? 2 theta? Oh, yes, that's the correct question. Is the 16 the same?
It says on the top where
Yes,
it's
it
why
is.
is it supposed to be a square cosine 2 theta?
Oh. Okay, so I obviously changed my notes to be accurate, but yeah, okay, cool. I obviously had a mistake. So this should be cosine 2 theta. Your notes are correct, my slides are wrong. So don't worry about changing anything, right? Are you with me? Okay, cool. Now, this here is going to be a little bit wacky, but let's just go through it step by step. So what about at theta equals 0? R squared is 16 cosine of 0, which is 16. Are you with me? 16 cosine of 0. So R is 4. Now, actually, this is actually going to generate 2 little parts of a graph at the same time. It's kind of like if I said x equals y squared, and then I gave you a table of x's. Wouldn't every time I give you an x that wasn't 0, you get 2 different y's?
Yeah.
Okay. Same is going to go here. Now, you could either say that x is 4, or r is 4, or r is
-4.
negative 4. All right? What about then Let's go to pi over 4. R squared is 16 cosine of pi over 2, if I take 2 pi over 4s, yeah? And what's cosine of pi over 2? 0. Now then, what happened at all these angles in between? Think progress. R was 4, and it went to 0, so it must have been smaller and smaller and smaller until it went to 0. So as it faced these angles, it went from 4 to a little less than 4 to a little less than 4 to a little less than 4, until when you faced pi over 4, it actually came out to be 0. You're down.
Yeah.
Now, keep in mind that R squared was 4 to 0, or 16 to 0, so R actually was also this other part. R went from negative 4 down to 0. Now, if it went from negative 4 to negative 3 to negative 2 to negative 1, then over here it also went from negative 4 smaller and smaller to 0. You with me, people? Okay. Now, say you put in pi over 2. R squared is 16 cosine 2 pi over 2, which is 16 cosine pi. 16 cosine pi is negative 16. Well, what do you make out of that?
No, yuck.
That's imaginary, okay? So there are actually no points in between negative pi over 4 until where this pi over 4 until this negative issue works out. When will I stop getting negatives and start getting into R squared is positive? Where over here, think here, at 3 pi over 4, R squared is 16 cosine of 2 times 3 pi over 4. What's 2 times 3 pi over 4?
0.
Cosine of 3 pi over 2, which is 0. Now, at this point then, that's where R squared stops being negative and starts being something again. And you'll start to get points again and again and again, getting bigger, going from 0, until you put in pi again, and R squared is 16 cosine of 2 pi, or 16, so R is again 4. Now, same goes here. Just like this was giving you positives, you could have also had R's that were negative, so you could have been backing up. So you also get this back here. And you'll see that you don't get any points in there. No, oops, I missed. No points in here also. From 5 pi over 4, 7 pi over 4, again, that's regions where R squared is negative. Okay, now that then is a lemniscate. It looks like a propeller or an infinite sign, yeah? Now, we know that when you do cosine, it's symmetric at the x-axis. So then when we get to this, sine should be symmetric at the y-axis. Would you draw up here this? Symmetric at the y? No. It is not, sadly. That's a general rule of thumb, but not a hard fast. Always true rule. What angle will the max R come at? Pi over 4. Why pi over 4? You're absolutely correct. Yeah, because sine is at a max when you take sine of pi over 2. Well, if it's sine of 2 theta, then it's got to be sine of pi over 4 times 2 to get that. So here you'll actually see propellers there, and there are no points in here from pi over 2 to pi, because you'll get r squared equal negative, and in this region 3 pi over 2 to 2 pi, again because you'll get r squared equal to a negative, because r squared equals to negative. You down? Alright, so lemniscate is characterized by, it feels like a rose because there's a 2 theta, but the square is what it's all about. Are you down? Graph these really fast, please. Okay, is it a lemniscate? What's the symmetry? How big? Oops. Is yours 2 theta?
Yeah.
All right, so sine, what angles do the propellers go along? Pi over 4 and 5 pi over 4, right? Is the max R 9 or 3? 3. So you should be going out 1, 2, 3, and here, right? 1, 2, 3. So it should look something like that. Yay? Okay, and so this is symmetric about the x-axis. What's the max R? 10, so surely you're going to have to change the scale a bit. Let's go by 2s. And 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Okay, you good? Okay. Area we don't have time for, so here's the thing. We're going to get cut up today. So this is what I need you to do. I want you to get out, set 150, 160, 170. And you're going to tell me all the questions you have. I'm going to work them or get you started on all of it, post it to my website. You're going to check them tonight and turn in all 3 tomorrow at the minimum, or today if you like. So first look at 150. Look, give me all your questions on 150.
3,
3, 1, 2,
8,
right here 4. Okay. 3, 1, 2, 8, 4.
12,
Did you say 12 or 20?
20,
20, 12, 25,
19.
19. I'll assume it's because no 7th hour. Okay, is that good for 115, or should we just do it all? 116. Would you also like me to help you put your name on the page?
You know, if you could.
Okay, 116, hit me. 23,
Six.
I hit 5, 5, 6, 8,
3.
3. Anything else on 116 you do not feel comfortable with?
11.
11.
I'm going to do my sense, and it's gonna be.
Hey, 116, we're good? 9? Okay. Anything else on 116? Okay, 117.
3.
3, 1, 20, 14, did you say? 19,
12.
12, 8.
17. 17.
Oh, I said 2017. Okay? Alrighty.
Thank you, Miss Lauren. You know, if you could do the rest too, that'd be great.
This is actually the first thing, just like you do your math first when you do your homework, because it's the most fun. When I do my homework, the first thing I do is make keys, because it's the most fun, then grading sucks.
So you could just not grade.
Honestly, for pre-algebra, not grading makes no difference, because they don't listen to what you write anyway, they just say, oh, I got an 8, blah, blah, blah. You guys, some of you actually look at the stuff I write. And then I gotta do it.
Thanks.
Sure. Okay, at the very least, let's crank out problem 2 now, shall we? Okay, so 115 we'll start with. Okay, so 115 number 3. Yep. Okay. So number 3, the couple things I could definitely see why you're iffy here. If you remember the problem back a year ago when you did it, it says a ball is thrown at an angle of 20 degrees at an initial velocity of 100 feet per second.
Yeah.
Okay, so I think you'll agree that when it goes 100 feet in a second, it doesn't travel 100 feet horizontally. Some of that is horizontal and some of it is vertical change, yeah?
Yeah.
So let's consider how much or how fast it's changing horizontally, which would be the velocity in the horizontal direction. How would you find it? By right triangle trig. What trig function would you talk? Cosine. So this is 100 cosine 20. Do you want to put your calculator in degrees or convert to radians? How do you convert 20 degrees to radians? What's the conversion rate? Do you agree it would be pi over 9? Okay, I don't like putting my calculator in degrees and I forget to put it back. I just radians. Okay. Do you agree that that tells you how fast it's moving in feet per second horizontally? That's the first part of the question. The second part of the question then says, neglecting air resistance, what's the horizontal displacement in 3 seconds? The horizontal displacement or change in position horizontally in 3 seconds would have to do with 2 things. How fast is it moving horizontally and how long does it travel? So isn't that just how fast it's moving horizontally and how long? So we're talking 100 cosine pi over 9 feet per second for 3 seconds. So 300 cosine pi over 9 is fine with me. Are you cool? And that's feet. Does that make sense? Okay, cool. 1, is 1 still a question? The height of a right circular cone is increasing at a rate of 3 centimeters per second. Don't forget your basics. On the AP test, it's expected that you translate that verbal statement and be intentional about the sign. So you're communicating that the height is increasing by saying the rate of change is positive. That's given. The radius is decreasing by 1 centimeter per second. That's given. And they want the VDT when the height is 10 and the radius is 4. You follow? Okay, so great. Now what do I do? Volume. You write the volume equation. 1/3 pi r squared h. You take the derivative with respect to time. Using the product rule, right? Okay. Okay, I will get the rest. Have a great day. Tomorrow, have, I guess, basically 4 sets for me. 15, 16, 17, and 18.
I can't.
Yes.
If one is negative, that's right.
If what?
Change the side.
Yes, that's fine. It is fine. Right.
Also, I'm signed up for your plans.
Okay.
How are we doing? Well, it's your turn.
It was an accident, Messiah. You gotta wash your hand now.
Yeah, you're right.
Was Messiah being yucky?
Yeah, I was.
Yucky. Yucky.